So in the last lesson, we looked at what the dot product was. Okay, so it's our first way of multiplying or doing the product between two vectors. What we're going to do today is just going to take a look at a couple of properties of the dot product. Okay, seeing how it compares with, say, some of the products or some of the properties that we have for regular multiplication, right? Commutative property, maybe the distributive property, things like that. Okay, so what we've got, and we'll just talk through a couple of these, which are pretty straightforward. We've got that the dot product itself, okay, by definition, we've got geometric, okay, so by definition, the geometric dot product is the product of the magnitudes and the cos of the angle between them, all right. Algebraically, the algebraic dot product, all right, is basically just multiplying the corresponding components together and then adding those two products together as well. So we can say again, yeah, this is a scalar quantity, all right. Is it commutative? All right. Can you do the dot A dot B? Does that equal B dot A? Well, the quick answer is yes. It's a very quick, simple proof, okay, of both cases. The geometric, you can really see that if we start off with A dot B, we have the product A, the magnitude A first, and the magnitude B second. Those are scalar quantities. So the commutative property holds true for scalars so that we can flip-flop the B and the A, and by doing that, we end up with B dot A. Okay, so the commutative property holds true. All right. If we were to try to prove it algebraically, on the right-hand side here, you can see the very similar result. A1 times B1 plus A2 times B2. Both of those are, all four of those numbers are scalars. We can do the commutative property for each of those, switch them around, we end up with B dot A. So the commutative law holds true for the dot product, all right? And we'll use that a little bit later as well, okay? One thing to take note of, we are using a dot, okay? So please make sure that when you're doing your vectors, whatever the vectors are, the dot product means something specific, okay? We're not going to be putting them together like we did with scalars before, all right? Or a scalar and a letter, right? 2a, we knew before, years ago, we knew that that was 2 times a. Well, we're not going to be doing it for vectors. Use a dot, okay? We cannot, at this time, use the multiplication symbol for the, basically the x between there, because this is not defined for vectors in 2 dimensions. When we get to 3-dimensional vectors, all right, we'll define what that actually looks like, okay? So we're not going to be doing that, okay, right now. Just only use the dot, all right? The distributive law. Distributive law, we use that probably starting, way back in grade 9. I think we did some of the distributive law here, okay, where you multiplied the number that was outside of the brackets by the 2 or more terms inside the brackets, right? So we multiplied that. What we're going to see is, does this distributive law hold true for vectors as well, okay, over the dot product over vector addition. So here we go. We got A dot B plus C, all right? So we're going to try to prove that, in fact, that should be A dot B plus A dot C, just like we did with the scalars, okay? Will it work? So we start off by using any vectors, so 3 vectors. We're doing this law algebraically, or the proof algebraically. So what we're going to do is we're going to set this up as written on the left-hand side, okay? So I'm going to throw this over to the side here so we can take a look at it a little better. So we have A dot B dot plus C, and specifically using the algebraic vectors A1, A2 dot B1 plus C1, B2 plus C2. Notice I just added the 2 vectors B and C together, okay? Now, when we do the dot product, We know that we're multiplying corresponding components together. So that is A1 times B1 plus C1 plus A2 times B2 plus C2. All right. These are scalar quantities. The scalar quantities are distributive, so that we can say that this is A1B1 plus A1C1. Also, A2B2 plus A2C2. Okay. We also know that the scalar are commutative, so that we can move these terms around. And if we move the A1B1 with the A2B2, you notice that this is the dot product between A and B. And when we move the A1C1 beside the A2C2, that is the dot product between A and C. Okay, so we just proved the distributive property. Okay, at least from one vector to the next. Okay, so we've got that. It's written out for you here as well. You can take a look at it. All right. The next distributive law is basically similar to what we started in grade 10, where instead of just having one term out front, we had two terms out front. Okay, so in this case with vectors, we're going to have two vectors. All right, dot product, two more vectors. These happen to be the same. All right, and we're going to take a look and see what it is. This one is very, very similar. If you can liken this to, let's say it's x plus y squared, right? We have the x plus y times the x plus y, and you know that that's x squared plus 2xy plus y squared. We're going to show that it's very, very similar using the dot product, okay, inside there. All right, so if you follow along, okay, with what we have using the dot product, all right, I said use the laws from above. We're going to be using partly the distributive property that we know, and we're going to take this as one vector itself, and so we can use the dot product with A, and then we can add that with the dot product with B as well, and so we have our first result there. Associative property, commutative property rather, we can move the dot product from left to the right side. Okay, so we're set that way. Again, we expand it one more time with the dot product. Okay, and you have all of these terms built in. All right, notice A dot B, B dot A is the same, so we have two of those, 2 times A dot B. All right, so we have our proven quantity that we wanted on this hand side. Okay, take a look at that, make sure you understand, all right, what you're doing there. What is A dot A? Well, if you think about it, if we know that A is A1, A2, A dot A is A1 times A1 plus A2 times A2. Well, that is A1 squared plus A2 squared. Well, that's just the magnitude squared, right? So you take a look at it. A dot A is the magnitude of A squared. It's a nice little, not definition, but a little property that you can be using. All right. This line is basically just taking this last line and changing the A dot A and B dot A or B dot B into the magnitudes. Okay, so it's another way of thinking about maybe solving a question like this. All right. Here's another way. Now, where do we come up with this? By definition, the geometric definition of the dot product, that is the magnitude of A times the magnitude of B times cos theta. So the magnitude, right? The magnitude of A plus B squared looks really close to the cosine law. The difference is it's plus instead of minus. And the reason why is the way that these are set up. The degree or the angle using the dot product is setting tail to tail. Cosine law is basically head to tail, as it says in here. So you've got your supplementary angle that's going in, which makes this property of the negative cos. So that's where you'd get your cosine law. So everything holds true. All right. What I want you to take a look at and understand on your own, I want you to pause the video so that you can go through this itself, is expand this out so that you can see that you will get this result. And the reason why is so that we can say this is you when you expand the dot product, you're using the exact same principles as when you were just expanding scalar quantities together. So all those things that you've been doing over the last couple of years, they work with including this dot. Okay? You can use the u dot u, or you can have the magnitude of u squared, right? V dot v, the magnitude of v squared, right? The magnitudes here with the angle between them, right? You can convert those in. So you can solve some of the questions that you're going to get, I know, right, in the homework quite quickly, quite easily, by using the same principles that you've already know how to use. All right? Now, the last idea, I'm going to take it through. You might have to pause a couple of times with this to understand. I'll try to work it out as best I can with you. Is called the projection of a vector onto a vector. It is a vector projection, okay? A vector projection. All right, what is this? And basically by setting it up, its usefulness, I believe, is a lot into gaming, setting up the games, having shadows, okay, on walls at certain angles, on the ground, on tanks, whatever type of games you're using. All right, because really when you look at it, if we set this up, take a look at the diagram. We've got OA is vector A, OB, the long one at the bottom, okay, is vector B. All right. Well, the vector projection of A onto B is perpendicular. It's like taking the sun right above the head of A. And what is the shadow that's cast onto B? And that's where you get this ON, okay? The vector ON. So the projection of A onto B is the vector ON. The head of A, all right, is perpendicular right over top of N. OAN is perpendicular to OB. All right, so that's the first part. That's just setting it up, knowing how to set the thing up. Now we're going to figure out what this all is. All right, so by looking at the definition of what ON is, we know that it's a scalar multiple of OB. All right, to be a scalar multiple of OB, you have to calculate it some sort of K. Okay, K, it's a K value, some scalar of OB when multiplied by the vector B will give you the vector ON. Okay, now your textbook is going to ask you for the scalar projection. Okay, at times, what is the scalar projection of A onto B? All right, and this is how you find out what it is, right? We know that ON, if you look at the triangle, and let me just take this off again. If you look at the triangle OAN, all right, you can see that you've got a right angle triangle, and the magnitude of ON, right, the magnitude is right there. It is the adjacent side of this right angle triangle to the angle theta, all right? And so we use cos theta in order to calculate, right? What the magnitude of ON is. All right, so when we simplify, okay, so if you've got cos theta equals ON over the magnitude of A, right? So when we solve for ON, we throw the magnitude of A on top, we get the magnitude of A times cos theta. Cos theta, by using the dot product, in this case here, is this bigger bracket. And we've used that before when calculating what the angle is. All right. And yes, because we're dealing with scalars, we can reduce the magnitudes of A, and we're left with the dot product of A and B divided by the magnitude of B. This is the scalar projection of A onto B, the scalar projection. Okay. And that's what the magnitude of ON is. Okay, we still have to continue on with what the vector projection is. All right, so let's continue. So here's the idea. Try to explain this through. We know that the magnitude of ON is some scalar quantity of the magnitude of OB. So when we rearrange this, we can figure out what the scalar quantity is. It's the magnitude of ON divided by OB. Well, we know what ON is, right? We just had that ON is the scalar projection. The magnitude of OB is the magnitude of B. So what we're going to do is we're going to divide the scalar projection by the magnitude of B. And when you simplify that, you've got your K value. Okay? It's the magnitude, it's the dot product of A dot B divided by the magnitude of B times the magnitude of B squared, which is, in fact, B dot B. So taking a look at this, we know that the projection, the ON, is a scalar quantity of OB. We now know that the scalar quantity, the K value, is A dot B divided by B dot B, and OB is the vector B. Okay, so that's where you end up with, this is the vector projection, as it says so right here. Okay, so this is the vector projection of A onto B. We write that down. We can symbolize that with this, a down arrow, and you can see it's the projection of A onto B. That's why the down arrow is there. All right. There's a couple of examples that you can look at. Make sure you understand them. Okay. You can see in this case, because you've got the projection is negative, you're going to have it in the opposite direction. You can see that, but what I want you to do is go through the process. It's just algebra. You've got the algebraic vectors. You're going to find the vector projection of A onto B, start off with the definition, and go through the numbers themselves. When you have the scalar, you can multiply it inside of the bracket. Okay? Go through those questions. Good luck.